Let me see. Can you hear me properly?
Yes, yes, we can
Okay,
hear.
very good. Okay, this is the last section of the part on information measures, and it's entitled Farnell's inequality. It's a very important inequality in the name of Bob Farnell. Okay, now before we prove Farnell's inequality, I would like to mention this very important theorem for you. It's very elementary. It says that the entropy of any random variable x is upper bounded by the log of the size of the alphabet. Okay, and this upper bound is tight even only if x is uniformly distributed on the alphabet. And we have seen this for the binary case. Where in the case of a binary random variable, the entropy is maximized when it is a uniform distribution between the two values. Okay, this carries over to a general random variable with a finite alphabet, and the proof for the interest of time, I'm not going to give you the full details. So basically, you only need to consider the uniform distribution and see that the difference between a log of the size of x and the entropy of x can actually be expressed as the divergence. Sorry about that. Can be expressed as the divergence between the distribution itself and the uniform distribution. Okay? And therefore, it is always non-negative. So basically, it's just that. Okay? So whenever the inequality is tight, it means that the distribution is uniform. Now, this theorem actually has some interesting implications. It means that the entropy can be as large as you want, okay? Because you can just make the alphabet larger and larger. But not only that, it also implies that the entropy can take any values, any positive values. Okay. The reason is that now, if you're making it uniform, you can make the entropy log 2, log 3, log 4, log 5, so on and so forth. But all the real numbers in between these discrete values can also be achieved. Okay. This is also implied by this theorem, which I won't get into the details. Okay. Another remark is that in a case that a random variable takes has an infinite alphabet, but countable, okay, entropy can be finite or infinite. Okay, it doesn't mean that it is always infinite. Sometimes if you have an infinite alphabet, but the entropy can also be finite. Okay, now Farnell's inequality says the following. Now the x and y be random variables taking values in the same alphabet. Okay. Now we're concerned about whether x and x hat are the same. When x is not the same as x hat, you think of x being an estimate of x. Right? But it doesn't have to be that way. X can also be an estimate of x hat. The argument is actually symmetrical. But let's say we are interested in x, and x hat is an estimate of x. Now here it says that the entropy of x conditional on x hat, which means that we are given x hat, and then we ask what's the uncertainty about the original random variable x. Now this uncertainty, according to Farnell's inequality, is upper bounded by the binary entropy evaluated at PE, where PE is the error probability, meaning that x is not equal to small x hat, plus PE times log of the size of x minus 1. Okay, instead of giving you a proof, I would like to offer you the following intuitive explanation. Now, here I'm given the random variable x hat, which is an estimate of x, and I ask what is the uncertainty of X, the original random variable that I'm interested in. Now here I'm going to remove this uncertainty by answering two questions for you. First, I'll tell you whether X and X hats are the same. Okay. Now with this, whether X and X hat are the same, which means that whether you've made an error or not. Okay. It is a binary question, and the answer has entropy equal to the binary entropy evaluated at PE. Because they with probability PE, then I'll tell you that they're not the same. Okay. So this is the for the first question, I remove some certainty for you. I tell you whether the two random variables are the same or not. For the and then in the next step, if I tell you that they are the same, then I don't need to tell you anything else. Then I already have removed all the uncertainty about X. Otherwise, in the next step, I'll tell you which one of the other possibility that X actually is. I tell you that X is not equal to X hat, so it must be one of the other values, and I tell you which one. And the uncertainty of the second question is at most equal to log of the size of alphabet -1, because using the previous theorem, the answer of the second question must be upper bounded by log of the size, the number of possibilities of the answer. Okay, so and then I only need to get into the second step with probability PE. That's why I multiply this entropy by PE. So this is the intuitive meaning of Farnell's inequality, and a simplified form of Farnell's inequality is the following. Sometimes we only need this. Okay, we upper bound the binary entropy by 1, and then instead of using size of X -1, we just use size of X, and that's good enough asymptotically. So that's also a very useful form of Farnell's inequality. Okay, so yeah, so I'm done with the Farnell's inequality. All right, so well, we come back to this when we talk about channel coding theorem in the next lecture. That's the lecture for tomorrow. So I'm done with information measures, and next I'm going to start another topic on the typicality. In the literature, there are two commonly used typicality. One is called the weak typicality, and the other one is called strong typicality. I'm going to talk about strong typicality. Now, so far, when we talk about these information measures, I give you some very high-level explanation of these quantities. Like, for example, entropy talks about the uncertainty of a random variables. The mutual information is about, when I tell you X, how much do you know about Y, that kind of thing. Okay? But these are very high-level explanations, and I haven't actually pinned down anything for you. But the notion of strong typicality actually is the first step toward pinning down the meaning of the physical meaning of these information quantities. Okay, so what does it mean by a typical sequence? So let's say we have a sequence X of K. K is a discrete index taking values 1, 2, 3, 4, so on and so forth. And where X, K are IID with a generic distribution Px. Now, X denotes the generic random variable with distribution Px, and with entropy Hx less than infinity. It's got finite entropy for each of these random variables. Now, if we consider a random vector of length n, X, bold X like this, then the probability of this random vector, because the components are IID, it is equal to the product of the probability of each of these random variables. Now, assuming that's it's finite alphabet for the setup of strong typicality, and that's the base of the logarithm B2, so that the entropy is in bits. Now, here's the some further notations. Now, for a particular sequence in the script x of n is a length n sequence with each components taking the values in the alphabet x. We let n small x of the sequence x be the number of occurrences of x in the sequence. Okay, I'm going to give you an example to illustrate this in a moment. Now, so this is the number of occurrences of small x in the sequence. You divide it by the length of the sequence, then it becomes a relative frequency of occurrence of this value in the sequence. And the collection of relative frequency is called an empirical distribution. It tells you which symbol occurs with what a fraction of time. Okay. Okay. For example, for sequence 1, 3, 2, 1, 1, and the number of occurrences of 1 is equal to 3. Oops, let's see. Okay, the number of occurrences of 1 is equal to 3. Because 1, 2, and 3 occurrences. And number of occurrences of 2 is equal to 1. Because 1 occurrence of 2. And the number of occurrences of 3 is again is equal to 1. And if you divide this by 5, which is the length of the sequence, you get this empirical distribution: 3 over 5, 1 over 5, and 1 over 5. All right. Now, the notion of typical sequence is like that. Now we define a strongly typical set, okay, with this somewhat complicated notation. Okay, T denotes typicality, and X is the generic random variable. Now delta is a small quantity, okay, which is to be specified, and N is the length of the sequences. So this is now the strongly typical set is a set of sequences of length n, okay, with satisfy a certain property. Now this is a so-called strongly typical set with respect to a distribution Px. It's the sequences of length n such that the following properties hold. First, if x is not in the support, namely that the p of x is equal to 0, then the number of occurrences in the sequence must be equal to 0. Which means it cannot occur. Okay? If the probability of a certain symbol is equal to 0, then that symbol cannot occur in that sequence. Okay. Requirement number 1. Requirement number 2 is that we consider the absolute value between the relative frequency of small x and the true probability of small x. Okay, and then you take the absolute value. Okay. Now so this is how much the relative frequency deviates from the true probability, and then you sum of all these deviations over all x, and it has to be less than or equal to this small quantity delta, which means that the relative frequency does not deviate from the true probability distribution by too much. That's the very meaning of a sequence being strongly typical. Okay. But delta is a parameter that you can control. Okay, and the sequences in this typical set are called the typical sequences, the delta typical sequences. All right. So some remarks. Now, because we are talking about finite alphabet, if this summation is small, then every term in the summation must also be small because it's a finite sum. Okay. Now in other words, if this summation holds, that's if the sequence is typical, delta typical, then there is some small quantity, then the relative frequency for each symbol is approximately the same as the true probability of that symbol, okay, for all x. Now this is true only. This is the case only when when we're talking about finite alphabets. When things are when alphabet is countably infinite, then it may not be the case, because the each one of these terms in the summation may be small, but they may sum up to infinity. Right? This can have happened. Okay, so this the third point is something I already explained. If X is strongly typical, then the empirical distribution is approximately equal to the generic distribution of the random process. Now, in particular, if X is strongly typical, then the probability of each symbol in the sequence must be strictly positive because of this requirement here. This requirement says that if a symbol is not in the support, then the number of occurrences must be equal to 0. So if it occurs, then the probability must be in the support. All right. Now the most important concept for typical sequences is this notion called asymptotic equipartition property. Now this is actually a very descriptive name, asymptotic equipartition property. Asymptotic means n is very large. So we're talking about very long sequences. Equipartition, as you're going to see, it means that all the sequences in the typical set actually have approximately the same probability. It's almost like a uniform distribution on the typical set. So the statement of AEP, which in this case we're using strong typicality, that's why it carries the adjective strong here. But if you just think of it as AEP again. AEP says the following: now, but delta is a small quantity that we control the deviation between the empirical distribution and the probability distribution. Now, delta is some quantity that we specify, and we can let delta go to 0. Delta can be as small as you want, and eta is a quantity that goes to 0 as delta goes to 0, and so there exists eta greater than 0 such that delta goes to 0 as delta goes to 0, such that the following holds. First, if X is a typical sequence, then the probability of that sequence is upper bounded by 2 to the power minus n times entropy of X minus eta. Eta is a positive quantity, and this is actually an upper bound because of the negative sign here. Okay? So it is upper bounded by this, so 2 to the power minus n times n, so entropy minus eta, and the lower bound is 2 to the power minus n times entropy plus some quantity eta. So essentially what it says here is P of X is approximately equal to 2 to the power minus entropy, 2 to the power n times entropy of X. Okay, this is what it says. Okay, this is what the first property says. The second property says that you're going to get a typical sequence with very high probability, with probability greater than 1 minus delta. The third property says that the number of typical sequences is approximately equal to 2 to the power n times entropy of X. Okay. So this is what it says. It's upper bounded by 2 to the power n times entropy of X plus some small quantity eta. It's lower bounded by 2 to the power n minus 2 to the power n times entropy minus eta, and then you multiply to this 1 minus delta, which can be as close to 1 as you want. Right? So essentially, what is says is that the number of typical sequences is approximately equal to 2 to the power n times entropy. So now what it boils down to is the following. If I have an IID process, I just draw the same random variable repeatedly, what I end up getting with very high probability, I'm going to get a sequence which is typical. And this sequence would have a probability approximately equal to 2 to the power minus n times the entropy. So this is what the strong EP says. Now the third property is just a consequence of the second and the first property, namely that with probability almost 1, you get a typical sequence where each typical sequence has approximately 2 to the power minus n times entropy as the probability, and therefore the number of these typical sequences is simply 1 over the probability of each one of them, namely 2 to the power n times entropy of x. So this is intuitively what the AEP says. Okay, so the proof idea is the following. Now, if x is strongly typical, then the empirical distribution is about right. Okay, about right meaning that it is close to the true distribution. Okay. Now, if the empirical distribution is about right, then everything else, including the empirical entropy, would be about right. The empirical entropy is that okay. Now remember that the entropy of x is equal to minus the expectation of the log of p of x, right? Okay, so this is the average of the quantity. So average of the quantity minus log of p of x. Okay, so this is what the expectation says. So if you, so in order to find out this the average of minus log of px, you can keep repeating the experiment. Okay, you repeat the experiment in an IID fashion for many times, and then you take average. Okay, then it would be, this is the so-called empirical entropy. Then because most likely the sequence will have the right relative frequency or the right empirical distribution, then as n becomes very large, then this will be very close to the entropy of the generic random variable. Okay. So now this is equivalent if minus 1 over n log px is approximately equal to entropy of x, then this says that p of x is approximately equal to 2 to the power minus entropy, 2 to the power minus n times the entropy. So intuitively, this is what the strong EEP is talking about. And in the interest of time, I'll just highlight the steps in the proof. The steps of the proof is nothing more but applying the weak law of large numbers. Okay, so it's a relatively simple application of the weak law of large numbers, which I won't bore you in the interest of time. Okay. Okay, so after all these things, you have the right setup, you end up having this. Okay? So this is the first property of the strong AEP, and so now the reason why we need to invent another quantity eta is that eta is taken to be minus delta times log of the minimum of px over all x. Okay. Now this is where we need the finite alphabet assumption, because if you if the alphabet is not finite, then this minimum does not exist. So eta is equal to this constant. This is a constant, okay, multiplied by well, this constant is equal to minus log of this this minimum probability, and so eta is equal to a constant multiplied by delta, and that's why eta goes to 0 and delta goes to 0. Okay. Now so this is the foremost. I mean this is second property. The second property basically is a consequence of the weak law of large numbers, and I already have given you the intuitive reason for that, and so I won't get into the details. Let's see. The third property again follows from the first property and the second property, but I would like to summarize what I have talked about in this picture. Now, this picture is important. Now, in information theory, it turns out that when we think about the asymptotics, it actually helps to think sloppily in the following way, but sloppily in the right way. Now here in this picture, the rectangle is the set of all n sequences, and the typical set is the set in red, and the dots are the typical sequences. Now, according to strong AEP, the size of the typical set is approximately equal to 2 to the power n times entropy of x. And now, if the entropy is strictly less than log of the alphabet size, which is the case whenever x is not uniform, then 2 to the power n times entropy would be less than, much smaller than 2 to the power n times log of the size of the alphabet. Okay, because when even though the difference may be small, but when n becomes large, then the difference becomes very large. Okay, and so 2 to the power n times log of the alphabet can be rewritten as 2 to the power log the size of the alphabet to the power n. And this is just the size of the alphabet to the power n, which is the size of all the sequences. So what it says here is that whenever the entropy is strictly less than, whenever the distribution is not uniform, so that the entropy is strictly less than log of the alphabet, the size of the alphabet, then the typical set asymptotically would be much, much smaller than the set of all sequences. And in fact, it's negligible. Okay? The size of the typical sequences is negligible compared with the set of all sequences. However, the probability of the typical sequences is almost equal to 1. It actually captures almost all the probabilities, all the probability in that. Okay, it's very strange situation. It is a asymptotically negligible set, but it captures all the probability, almost all the probability. And not only that, but the probability of each of these typical sequences are almost the same. Is approximately equal to 2 to the power minus n times the entropy. And that's why it is called the asymptotic equipartition property. Okay, it's because inside the typical set, you almost have a uniform distribution. So that's the meaning of asymptotic equipartition property. Okay. All right. So here's a very important consequence of the strong AEP. It actually renders a very simple proof of Shannon's first theorem, namely the source coding theorem. Now, so the setup is like this. We have an encoder, which we first have a source sequence X, which is an ID source with length n, okay? And then we feed it to an encoder, and it encodes into an index, which is the function of the sequence. And then based on this index, the decoder would decode a reproduction sequence, which hopefully is agrees with the source sequence with very high probability. Okay, let's see how we can do this. Now, so for this source sequence, we assume that it is an ID information source with generic random variable x. Now, in n times loss, the source outputs a random variable, a random sequence, okay, of length n, and now we index the sequences in the typical set starting from 1. So the indices are 1, 2, 3, 4, so on and so forth. And according to the strong AEP, the number of indices we need to index all the sequences in a typical set is approximately 2 to the power n times the entropy of the generic random variable. Now, so this is how we do the encoding. If the sequence, the source sequence, happens to be typical, then we transmit the index of this sequence in the typical set. If the sequence happens to be atypical, then we transmit a dummy index 0, because all the indices of the typical sequences start from 1. Okay. So what happens is that when the decoder receives the dummy index 0, it declares an error. I cannot decode. Okay. Otherwise, based on the index received at the decoder would be able to recover the source sequence, which is one of the typical sequences. So this is the performance of the source code. Now the rate of the code is equal to log of the size of a typical set plus 1, because you need a dummy variable, a dummy index 0, and then you need log 2 of that that many bits to represent the index. If you use 2 as the base of logarithm, and then the rate is equal to this logarithm divided by n. Okay, now because this is asymptotically, this is approximately equal to 2 to the power n times entropy of x. Okay? And then you take the logarithm and then you divide it by n, and you get back entropy of x. So the rate is approximately equal to the entropy of the generic random variable. And also by strong AEP, the probability of error is almost equal to 0, because most likely you won't get an atypical sequence. And then if you get an atypical sequence, you are very unlucky, and then you end up having a decoding error. But that will happen with very, very small probability. So this is already in fact, the direct part of the source coding theorem, which is actively an informal discussion. And so you see that the source coding theorem really justifies the notion of uncertainty of the entropy. Now, the converse part of the source coding theorem, which I won't cover here, is that if you use a rate strictly less than the entropy of x by small quantity, no matter how small, which doesn't change with n, then no matter how clever you are when you do the data compression. By the way, this is called data compression. Okay? You compress instead of using okay, if you don't compress, then you need to use a rate equal to the log of the alphabet. This is the rate that you need to use, because if you encode everything in the set of all sequences, you take the logarithm and then you divide it by n, you get the log of the size of the alphabet. Okay? This is the full rate, the uncompressed rate. But now we have a better way, with a more clever way, and then we only need to use this as the rate, okay? Which is strictly less than this. Whenever the whenever the source is not uniform. If the source is uniform, there's nothing you can do. There's nothing you can do. Okay. So now if the converse of the source coding theorem says that if you use a rate strictly less than the entropy, then the probability of error would tend to 1 as n tends to infinity, no matter how clever your compression algorithm is. Okay? So the entropy is the definitive dividing line. Anything for data compression, you must use a rate at least equal to the entropy. Otherwise, you're going to fail. Okay? Fail miserably. Okay, the probability of error actually will go to 1. Okay, so I think if I overrun a little bit by maybe 10-15 minutes, I would be able to cover this joint typicality. Would that be okay? Because because we need this for tomorrow. I mean, the information measures and typicality is a very aggressive syllabus for 2 hours, but I'm trying my best.
Yeah, we have 30 minutes or so. No
okay.
problem. Total, yeah.
So joint typicality is about the notion of typicality when you have a pair of random variables. When you have one single random variable, you talk about typical sequence, but you have 2 random variables, and then you repeat the experiments. Then we need some notions of a joint typicality. Okay, here's the setup. Instead of having one random variable, we have a pair of random variables, x, k, y, k equals 1, 2, 3, 4, so on and so forth. And where this pair of random variables are ID with a generic distribution. And as before, we use x, and we denote a pair of generic random variables. But this time we need 2. Okay, we denote them by x and y with a joint entropy being finite. Okay. So x and y xk and yk, xk, yk, and xj, yj are independent, but they are independent copies of each other. But x and y may not be do not need to be independent. In general, they are not independent. So we also assume that both x and y have finite alphabet. And so I mean that we just extend the previous notation. We let this notation be the number of occurrences of x-y pair in the pair of sequences. Now we consider a pair of sequences, both x, both y. These are length n, a pair of length n sequences with the first sequence taking values in x, and the second sequence taking values in y. So for such a pair, we use this notation to denote the number of occurrences. And if you divide this by n, you get the relative frequency of this pair of symbols in the pair of sequences. And then this collection is called the empirical distribution of the pair of sequences x, y. Now here's a quick example. So in this case, 1, 2, 3, 4, 5, 6. N is equal to 6. Okay, length is 6, and x is this sequence and y is this sequence. The number of occurrences of 0, 0 is equal to 1. It's only one occurrence. And the number of occurrences of 0, 1 is equal to 2. Number of occurrences of 1, 0 again is equal to 2, and number of occurrences of 1, 1 is equal to 1. Okay. So the definition of strong typicality is a strong joint typical set. It's actually something you would expect, right? So as before, for any pair of symbols which is not in the support, then they cannot appear in the sequence, and then the deviation of the total deviation between the empirical, the relative frequency and the true probability must be less than some delta. Okay, so it's the same thing as before, nothing new. However, because we are dealing with two a pair of random variables, there are certain things that we need to take care of. First of all is the consistency property, meaning that if a pair of sequences are jointly typical, okay, then each one of them must be typical with respect to its margin, with the marginal distribution. Okay, so we want this kind of consistency. Otherwise, it's very difficult to discuss. And then another similar property is preservation. If X is a if X is a typical sequence with respect to its own distribution, then if f of X is a Y sequence, okay, obtained by this. Each yi is a function of xi, where the function f doesn't change. So x1, you take a function f becomes y1, x2, you take a function f becomes y2. Okay, then then this derived sequence is again typical with respect to the distribution of y, where y is when you take a function of a typical sequence, then the sequence remains typical. Okay, here's a joint AEP. Actually, it's the same thing as the original AEP, except that we replace X by a pair of sequences XY and also a pair of random variable XY. There's nothing new in the strong AEP. So what is really new is the next one. Okay, it's something that what we're going to talk about, call it conditional AEP, conditional AEP. Okay. Before I talk about this, I would like to draw your attention to Stirling's approximation, okay, which is a very basic result in mathematics. It says that the n factorial, it doesn't have a closed form. Okay, if you calculate n factorial on your calculator, it blows up very quickly. However, if you take the natural logarithm of n factorial, it turns out that it's very close to this closed form expression, n times natural log of n. So I'm not going to get into this due to the interest of time, but it's elementary. Okay, so okay, one important consequence of Stirling's approximation is the following. So we have this this binomial coefficient, right? So so n choose so n is a large integer, and p is some probability between 1 and 1 minus 1 and 0 and 1. Okay, so so n choose np comma n times 1 minus p. We assume that these are integers as well. Okay, so this is just I'm sorry. So this is just oops, I cannot put my hand on it, fortunately. N choose NP basically. Okay, so it says that the n choose NP is approximately equal to 2 times the binary entropy of this binary distribution. Okay, this is a very important consequence of Stirling's approximation. So more generally, if you have the consider the multinomial coefficient, then okay, more generally we have this. For the binomial coefficient, we have this. for the multinomial coefficient, so we have a distribution P1, P2 up to Pm, and then we have this multinomial coefficient. It is approximately equal to 2 to the power n times the binary entropy of this distribution. Okay, so this is something that we're going to make use of. Okay, now the conditional strong EP says the following. For any typical sequence X with respect to its own marginal distribution, we let this set, which is now even more getting more complicated, is y given x, okay? N and the delta remains the same. Now here you are you're given a typical sequence X, and then you consider all the y's that are jointly typical with this X. Okay, so we are given a typical X, and we ask what are the y sequences that are jointly typical with that X. Now this theorem, the conditional strong EP says that if there exists at least one such y, which is typical with that X, then the number of y's that are typical with that X is approximately equal to to 2 to the power n times the conditional entropy of y given X. This is what the conditional strong EP says. Okay. Now, what this theorem is surprising or not surprising, right? The number of jointly typical sequences is approximately equal to 2 to the power n times the joint entropy, right? The number of typical X sequences is approximately 2 to the power n times the entropy of X. So if you divide this by this, you get the average number of typical sequences with a typical y with a typical X on average. Okay, so this is now you evaluate this, and it turns out to be 2 to the power n times entropy of y given X. So for a typical X, on the average, there are not a fixed one, but the average over all typical X sequences. The number of y's that are jointly typical with a typical X sequence is approximately 2 to the power n times entropy of y given X. Okay. Now, then the conditional strong EP actually says that this not only holds on the average, but it holds for each typical X, as long as there exists at least one y that's jointly typical with that X. So it is surprising, but not surprising, but also surprising in a way. Okay? Now, the proof of the lower bound is actually quite easy, but the upper bound calls for some counting. Okay. Okay, the lower bound calls for some counting. So I'm going to give you the idea for a very simple case. X is a binary alphabet and Y is a ternary alphabet, ABC, okay? So let's say we have a typical X sequence so that the number of zeros is approximately equal to n times P0, and the number of y's is approximately equal to n times P1, okay? Now, suppose we are able to find a y which is typical with this X, right? So, and the number of A's, number of 0A would be approximately equal to n times P of 0A. The number of 0B's would be approximately equal to n times P of 0B, so on and so forth, right? So now here we, so each of these number of occurrences would be about right, okay, n times the true probability. Now here we, I draw the diagram such that, draw the picture such that all the zeros occurs on the left-hand side and all the ones occurs on the right-hand side. But this actually doesn't matter, even if they're not like this. For the purpose of counting, of the subsequent counting, actually it doesn't make any difference. I just rearrange the zeros and ones in this way so that you can see it clearly. Okay, so now let's focus on this, on the zeros and also the A, B's, and C's that happens together with the zero. Now and also we focus on this. Okay. Now the number of you can shuffle the A, B's, and C's within these entries, okay, without changing the number of occurrences of 0A, 0B, and 0C, right? You can shuffle them within this, right? This range, and the number of ways that you can shuffle A, B, C's within these number of entries n times P0 is equal to n times P0, and then this is a multinomial coefficient, and downstairs you have n P0A, n P0B, and n P0C, right? And then the same thing here, the number of ways that you can shuffle the ABC within this one section is given by this. Okay? Now then you apply the Stirling's approximation, and then with some after some manipulation, you find that it's actually equal to 2 to the power n times the joint entropy, the conditional entropy of y given x. Okay, nothing too mysterious. It's just the Stirling's approximation, but the result is very important. Okay, so this actually proves that the lower bound. Okay, so the lower bound says is approximately equal to 2 to the power n times the entropy of y given x. The upper bound is also approximately equal to this. So we say that. So we see that the typical conditional typical sequence is approximately equal to 2 times the entropy of y given x. Okay, now so this is a further illustration of conditional strong EEP. Here we have this is a set of all typical sequences. Okay, each one of them is as long as you can find. So the line means that this y is typical with that. Okay, as long as you can find one such line, then you will find approximately 2 to the power n times entropy of y given x lines. Okay, and same thing if you fix a typical y. As long as you can find one x which is typical with that y, then you would find approximately 2 to the power n times entropy of x given y x's that are typical with the y, with that y. Now, the next picture is even more. Well, I'll skip these fine details, but the next picture is actually even more important. Okay, so this shows this notion of joint typicality. So so here in this array, the rows are labeled by the typical. Well, don't worry about this S. Okay, there's some fine details. So just think of this as the T. Okay, I'll neglect the fine details at this point. So basically the columns, the rows are labeled by typical X sequences, and the columns are labeled by the typical Y sequences. Not just the typical Y sequences, but the typical Y sequences such that you can find at least one typical X which is jointly typical with that one. Okay, so what it boils down to is like this. Okay, the number of the number of rows is approximately this, 2 to the power n times entropy of x. The number of columns is approximately 2 to the power n times entropy of y. And then for a particular x, the dots on this row denotes those y that are typical with that x. And for a fixed typical y, the dots on the on this column are the x that are typical with that y. Okay, so as long as you can find, okay, now the total number of dots is approximately equal to 2 times the entropy of the joint, 2 to the power n times the joint entropy, okay, by the joint AEP. Okay. Now, so you would expect that the number on average, the number of dots on each row would be approximately 2 to the power n times the entropy of y given x. The strong conditional AEP says the following. It says that for every row, as long as you can find 1 dot on the row, then you'll find approximately 2 to the power n times entropy of y given x dots. Okay, and then you see that every row has approximately the same number of dots. And for each column, okay, as long as you can find 1 dot, you'll find approximately 2 to the power n times entropy of x given y dots. And then if you go from one column to another column, you'll find that each one of them has approximately the same number of dots. Okay? It's a very peculiar combinatorial structure. Okay? You go vertically, you find that each column has approximately the same number of dots. If you go horizontally, each row has approximately the same number of dots. Okay. Now this is a 3-dimensional case. If you have 3 random variables x, y, and z, so this is the typical x's, this is the typical y's, and this is the typical z's. Okay. So if you fix a z to z naught, then you consider taking the slices, right? In this fashion. Okay. You look at the slices. Each slice has approximately the same number of dots. If you fix x naught and y naught, you're talking about this cylinder, okay? And then it's kind of like poking into the cube, and you find that every column has approximately the same number of dots. So this is a 3-dimensional generalization. Again, very peculiar structure. And we actually, this is the joint work of Terence Chen and myself in his master thesis, and we give it the name quasi-uniform array. And so with this, I'll stop my lecture for today. So I hope I have explained to you this notion of strongly joint typicality suitably, I hope. Okay, so I think we can still have a little time for Q&A.
Bikash, you are muted.
Yeah. So yeah, if anyone has a question, you can either raise hand or unmute yourself, I think.
Oh, by the way, maybe I want to say a few more words on this. In this picture, okay, so here, maybe okay, so here, if we have a typical X sequence, then we have approximately this number of the typical Y sequences, right? So if you are given a you know the X sequence, but you're also interested in knowing the Y sequence, then with a very high probability will be one of these 2 to the power n times entropy of Y given X sequences, and the number of bits that I need to tell you which one of them is approximately log of 2 to the power n times entropy of y given x, and then you divide by the rate is just multiply this logarithm by n, and this would be approximately equal. This would be equal to entropy of y given x. Okay, so bits. Okay. So this is the rate that I need to use to convey to you the y sequence that actually occurred. Okay. So this is also in some way an extension of the notion of uncertainty. So we are talking about conditional uncertainty. Right. So intuitively, it is also satisfactory because if I know x, then the uncertainty about y is given by the conditional entropy, and this also actually serves as a justification of this interpretation.
Thanks, Raymond. Perhaps you can quickly explain what quasi-uniform means here to the audience.
Oh, okay. Let me explain this again. Quasi-uniform means that if you take, well, this is an asymptotic quasi-uniform. Okay, actually, if you look at all the columns, they all contain about approximately the same dots. You look at all the rows, each one of them, they all contain approximately the same number of dots. Now, I'll give you one more very striking interpretation of this array here. So the number of dots approximately equal to 2 to the power n times the joint entropy, right? And the number of rows approximately 2 to the power n times the entropy of x. Number of columns approximately 2 to the power n times entropy of y, right? So obviously, number of dots is upper bounded by number of rows multiplied by number of columns, right? Obvious. And so it means that 2 to the power n times entropy of xy less than or equal to 2 to the power n times entropy of x times 2 to the power n times entropy of y. Okay, and if you take the logarithm and divide everything by n, you get this, which is the independence bound of entropy, or equivalently, I xy is greater than or equal to 0. So in fact, this is another big story. In fact, by studying such asymptotic equipartition, asymptotic quasi-uniform arrays, as shown in the Terence Chan's master thesis, you actually can obtain every possible entropy inequality. Okay. Not only that, but this quasi-uniform structure is tightly connected to group theory. So these are another big story, which I won't have time to cover. Which I will touch upon this to give you some highlight. I'm going to touch upon this in my final lecture.
Thank you. So, any questions from audience?
Okay, there is a question in the chat box. I'll just read it out. Or can you see it?
Let me see. Let me check.
Okay, it says, are we only considering discrete variables in this lecture?
Yes.
If so, what are the difficulties when some properties for example, inequalities, AP apply to continuous random variables?
Yes, but things need to be treated more carefully. Yes. Yes, but in this lecture, we only cover discrete random variables. Oh, by the way, for continuous variables, we for those of you who know the differential entropy actually is not always non-negative. Right? So unlike the discrete case, only the non-negativity of mutual information holds. And in the continuous case, the differential entropy is not equal to the self-information. So there's a distinction.
There is another question in the chat box. It reads, what is the single dot? What does single dot mean?
Oh, the single dot means
the
that
intersection of,
the single dot means that you look down this row and look down this column. Maybe I'll get rid of this again. Okay. Okay. The single dot means that if you look down this row and you look down this column, this X and this Y are jointly typical.
Okay, any other question from students, audience?
Hello. Okay. Am I audible?
Yes, I hear someone.
Yeah. So like if that single dot is that joint typical, so that is a joint typical with that particular X. Now the total number of dots are the total number of like jointly typical with all X and all, something like that. That green color. So the dot in the green color regime. So that is the jointly typical sequence with that particular X. Now, if I consider all X, like then the total, like what are the total number of dots in that rectangular regime? So
you mean
total number of sequences.
You mean the number of dots in this column?
No, like the total number of dots in the total rectangular box.
Oh, in the total rectangle, that would be approximately 2 to the power n times entropy of xy. Yeah.
So that is also the jointly jointly typical jointly typical sequences, right?
No, this is the this is the total. So this is actually the size of this jointly typical set. Yeah.
Okay. So like then the total number of dot means the total number of jointly typical sequences.
Correct. Yeah.
And then that the dot in the green regime is that total number of Y that is jointly typical with a particular X.
Okay. If you look at a particular X, you look horizontally. If you find a dot, it means that the corresponding Y is jointly typical with that X. If you don't find a dot, it means that the corresponding Y is not jointly typical with that X.
Okay. Okay.
Okay, there is another question by Kartik AK, which says, initially we had seen the introduction to entropy mathematically. Let us say we are getting entropy is equal to 2.5 bits. What does it mean physically?
Let's say we're getting entropy equal to 2.5 bits. So what does it mean physically? It means that if you have an IID source, information source, where the entropy of the generic random variable is equal to 2.5, then you only need 2.5 bits per to compress each symbol.
So the question goes on and it says, how is 2.5 bits represented? Isn't it meaningless? So I think
2.5 bits represented. Okay. Are you talking about a fractional number of bits? Is that what the question is?
I think that is what probably he's
okay, think of it this way. You use 5 bits to compress 2 symbols. So on average, you use 2.5 bits to compress each symbol. Yeah, the rate is just the average. Average over the number of n symbols. Welcome.
Okay. Any other question? Okay, I don't see anything else in the chat box. And we are also close to time. So perhaps we can stop here and meet again tomorrow.
Okay, very good. I hope to see all of you tomorrow.
Yes. Thanks, Raymond.
Okay.
So everything is nicely explained, how combinatorial ideas, probability, and set theory and information theory ideas are all have relevance to each other, and all these things makes the basis so that when we will go to the next part, when discuss channel capacity and other concepts. So this is very important. So I would suggest that you also go through the books, students particularly, and then practice these things. Yeah. Thanks,
tomorrow
Raymond.
we talk about we're going to talk about the channel coding theorem that will give the physical meaning of mutual information.
Thank you, Raymond, and see you tomorrow.
Thank you,
see you tomorrow. Thank you.
Bye.
Bye-bye.
Bye.